Wow, what the heck? Weird. Yeah, that looks better. Okay. Man, when I first looked at this quiz, I was running from a stupid meeting, and I whipped it out to you guys. I thought it said 0.01 formal KOH. What an easy quiz. I'm being so nice, right? And then so I looked at it again, and I saw the 5 times 10 to the negative 3. Oh, my gosh. Is it KA? So there, another mistake, right? Because you don't use the KA. You use the KB. And nice, because that's 10 to the negative 12 or something, right? So you can drop the X. All right? So nice. So twice I looked at this quiz and I messed up in my brain. But I think I saw a lot of answers that were like 7.15. So maybe that's right. I don't know.
I got like 6.9.
Okay. So we'll see. Let's leave that on. Okay, so we are talking about buffers. How to prepare them, how to pick them, and how to use them. I think we're going to be spending 3 days on buffers, so they're a big deal. You can tell they're a big deal. I mean, look at this. They're all over the place, right? And here's and every single cell has a buffering system going on here, right? I call this a buffer, H2PO4 minus and HPO4 minus 2. We'll see why it's a buffer. I say this is a buffer, carbonic acid mixed with bicarbonate. Okay. You have all these other buffers all over the place. Stabilizing hair, boric acid, calcium carbonate. They're all over the place. Buffers are a really big deal. If you didn't have buffers, I mean, I guess the poor lady would get sick. But the purpose of a buffer. Don't have too many of these, so Pablo, the purpose of a buffer is what? Ooh, changes in pH. Okay. All buffers, Erica, all buffers are mixtures of. Are mixtures of what? Well, they're mixtures of acids and bases. But technical term, they're a mixture of. No, say what you just said. I think. Conjugate acid and a conjugate base. Conjugate acid and a conjugate base. Now, the book didn't have the 5-step program either. Conjugate acid, conjugate base. There's always one in a buffer, right? You have a conjugate acid and a conjugate base. Every single time there's a conjugate acid and a conjugate base. So, if that's what a buffer is, Kathleen, how does a buffer resist, how does it accomplish its task of resisting change in pH? How does it do it? How do buffers accomplish their task? How does it work? Balance out equilibrium. We're getting close.
Well, the conjugate base is H plus.
Good. If you drink a whole heck of a lot of Coca-Cola, increase your acidity, right? Your conjugate base is going to react with it, right? Eat something basic. Tums, calcium carbonate, right? I don't know, eating a lot of basic foods. Your conjugate acid, whatever it is, we had them on the previous page. We'll take care of it, right? Yeah. So the conjugate acids are going to react with whatever base you have to maintain the pH. The conjugate, what's the other one? The conjugate acid reacts with any basic stuff. The conjugate base reacts with any acidic stuff to keep the pH constant. Okay. So it's just That's how it works. There has to be an acid to react with base. There has to be a base to react with acid. And the buffer takes care of it because they're both there. Conjugate acid and a conjugate base. So
So will the acid balance each other?
if you have any, somehow you increase the number of hydrogen ions, increase the acidity in your system, right? The conjugate base is going to react with it, right? And it just, right? It forms. Remember, so the conjugate base reacts with it. You have less conjugate base and more conjugate acid form. So you're going to be a little bit more acidic, but not that bad. Because is this a strong acid? No. So by adding an acid, you are going to still be somewhat a little more acidic, but the pH isn't going to skyrocket like it would if you added HCl and water or something. The pH is going to stay relatively the same. It's going to bump up 0.01 pH unit, or a really small amount, increment, but not that much. The buffer's resisting those changes in pH, whether they're going up or down. Does that help, Nyla? Okay. So when you're talking about buffers, ice will always work. I'm telling you, ice will always work. And you can set up the whole ice, and you have the Ka, right? You look up the Ka for the conjugate acid, whatever it is, and you can do the whole ice thing and get pH. But man, it is so much faster to use the Henderson-Hasselbalch equation. If things are rearranged, and it's just so much easier. So this Henderson-Hasselbalch, it comes from ice, but it's just rearranged and solve for pH. Solve for the negative log of the hydrogen ion concentration. Solve for the negative log of X in ice to make life so much easier. Okay? So, Urandi, we know what pH is, but what's pKa? What are you going to find in the table? You'll find the... You can find the Ka of the acid. Then what's pKa? Anybody help her? The negative log of the Ka. Right? Oh yeah, say it with, what do you call that? With confidence, and don't mumble it. Negative log of the Ka. Right. Now this technically should be not moles of the conjugate base and moles of the conjugate acid. It should really be what? Concentration. Why did I change it? Or Casey, is this just something Smith can do? Or is there a reason that you can actually change this to moles over moles? I don't know. Is it use concentration? You're getting there. What cancels? The liters, right? Because it's moles per liter. Liter unit just cancels on you. You can divide it by the exact actual amount of volume, but it's the same solution. These guys are in the same container, same volume. So a lot easier to use it this way. So that's the equation we're going to be messing with. So it's not the equation, I think. They might have concentration. I say use moles. It's a lot easier. Cat, when the volume of a buffer changes, the ionic strength changes. Why? When the volume of a buffer changes, the ionic strength changes. Right? It's more dilute, the concentration's changing, and that's how you calculate ionic strength, right? The concentration times the charges. Okay, so the volume changes, ionic strength changes, for sure. Therefore, the pH changes. So, do you get that? Before you even move on. You have blood, or whatever, right? you change the volume of it just by adding, who knows, it doesn't have to be solvent, it could be anything. Just change the volume. You're changing the ionic strength, you're changing pH. So you really, but concentration's changed. The volume cancels. So this is really best to use what in the Henderson-Hasselbalch? Do you see the problem? If we add, the pH changes, volume cancels here. It's gone. But yet the pH is changing. You got to use activities. All right? Then you're okay. Use activities. Appendix G, page AP11, lists a whole lot of weak acids and their pKa values. So if you don't believe me, just flip it open, right? No one brings their book anymore, I don't think, right? But there's a whole bunch of, I think they give you the names and the formulas and all this stuff. How do you pick a buffer? Right? You're supposed to use that table to pick a buffer. Let's see. What is to me, the answer is here. What is the purpose of a buffer, any buffer again? So the pH won't change, right? Well, by much, good, right? Okay, so these guys are in equilibrium, conjugate base and conjugate acid. But kind of think of them in terms of moles or population, actual molecules of them. Think of them in terms of population. When would the buffer be most effective? Right? You're going to make this stuff. You want the pH to stay here. What would you want in regards of population of these two? What's that? Well, you're always going to have equilibrium, but the population of them. You could have more than one or the other, right? Would you want more of HA? If you have more of HA than A minus, then you're betting on the fact that you're going to be adding some base. But you don't know. You're just making a buffer, right? Because the buffers, you'd want what populations? A whole lot of A minus? Then you're betting that acid's going to be added. Both, to have them pretty much the same, right? If they're the same population, then that's about as good as you can get. Because if you add some acid, okay, at least I have some A minus there. If I'm going to add some base, I got some HA there. So you want roughly the same, right? That's, I guess that you call that in the middle of your buffer effectiveness range or something, right? You're right in the middle. That's the best place to be. Well, if these guys are the same population, are they the same number of moles? Yeah, because isn't that what moles is? A mole is how many? Oh, so we're off by one. 6.02. 6.02. Isn't it 6.022? That's what I was shooting for. That's like she said 6.023. 6.022 times 10 to the 23rd. That's why I'm not giving you this cat. But, okay, so these are populations. They're the same. This is the log of what number? 1. What's the log of 1? 0. So pH equals pKa. When you're right in the middle, that is the answer to this question. How do you pick a buffer? Well, what pH do you want? 8.5. Maybe that's where this chemical process works the best. Or that's where the container doesn't deteriorate. I don't know. 8.5. You want the pH to stay there. Well, you go down that list and find a buffer that has a pKa closest to 8.5. Okay. And maybe the one closest to 8.5 is super expensive, so you pick the next closest one, right? But that's the idea. Is you pick the pH, you pick the pKa closest to the pH that you want, right? And that's the game that you play in picking a buffer. Okay, so you went through all that work to pick a buffer, and you found it. You know the pH you're at. You want to be at 8.5, so if we had that nice big table, we could have actually picked a buffer. But it's not. You just kind of get them to match. So we picked a buffer. And then how do you prepare it? It says to know this. So hint, hint. Okay, how do you do it? 3 steps. Mass the necessary grams of buffer, then dissolve in water. Well, necessary grams. Well, I guess that must mean that, dang, I want 250 milliliters of... You have to know the volume and the concentration of the stuff. 0.18 molar general buffer HA, right? You know how to get grams out of that, right? Do you see how to get grams out of that? Convert the mils into liters, and then multiply it by the big M, so liters cancel, then convert the moles to grams. So we can get grams. So they have to, you can't mass the amount of grams unless you know the volume and the concentration. So that's just assumed that you know what that is. Right? So you mass out the grams. All right? Then dissolve it in some water. And then you add small amounts of strong acid or strong base and stick a little pH meter in there. Adjust it to the desired pH. What if you go too far? Right? I want the pH to be 8.6. So I dump the solid in the water, get it all to dissolve, right? I want the pH to be 8.6. I'd make a couple drops of concentrated NaOH. Oh, shit, it's 12.9. No one noticed. Right? How do you get it? Do you just screw everything up? Add some acid. Okay, add some concentrated acid. 2.9. Oh! Right? You just keep adding acid and base. Are you screwing up the buffer? No, you're just messing around with the what? The population ratio. That's all you're messing around with, right? So once you finally get the pH to be where you want it, because its population is where it's supposed to be, and if you pick the buffer the right way, so the pH matches the pKa, these moles are going to be the same, or really, really close. Okay. And then, once you get the pH to be right, and then dilute it to, the final volume with pure water. The pH won't change too much if you're just adding water. Okay. I want to take a look at this guy. Yeah, they are. Oh, no. This buffer system. That buffer system, Miriam. What's my conjugate acid and what's my conjugate base? The conjugate, he's the acid or the base? You said he's going to be the base because he's reacting with the H+, right? He's my conjugate base. He's my conjugate acid. Now, the reason why I'm pointing this one out is that, do you have to have things be neutral? No, right? So that kind of leads you to this question that we're at. You have all these buffer systems. That means there's a conjugate acid and a conjugate base form. And, Jeff, you're supposed to name them. You name them all. If you give any name to a buffer, you're referring to its acidic, basic, or neutral form. What's your guess? Neutral. It's the neutral form. Key, remember this. This is a big deal. This is going to kick your butt next class period if you don't remember it. All weak acids are named according to their neutral form. There's no charge. And that corresponds to the name. The form that has no charge on it is the name. Okay. So let's practice this a little bit. We are going to need our chart. Dang, I should have scanned it because no one has their book, right? I have my book, but I'll have to give it to somebody. But it's not going to help you. Help everyone who doesn't have a book. I'll scan this for next time. But I think I said AP 11. Okay. AP 11. Okay, AP 11 looks like this. Acid dissociation constants. And what I want us to do is determine whether this name corresponds to the HA form or the A- form. Is it the conjugate acid or is it the conjugate base form? So you look at this guy, you try to find formic acid. So I'm going to give him to somebody. And we're in the A's, the E's. Where's formic acid? Oh, there it is. Okay. It says the formula is, does it have a charge on it?
No.
No, it doesn't. Now, what's listed here, this is the part that you really need to keep an eye on. What's listed here is always, see all the blue H's? See all the blue H's on there? Right? So always what's listed is the acid or the base form. It's the acid form. See all the blue H's. Okay? So you look at the structure. Now you're going to look them up in the table. And you look in here. If you do not see, do it this way first. If you do not see a little plus or a little minus, right? If it's neutral, you know that the acid form corresponds to the name. Right? If you we'll go on to the other possibility when we get to it. So let's just do that. This formic acid, does it have a little charge on it? No. So that means he's the guy that's in the table with the big blue H. So he's got to be the acid form. So you could write acid or just write HA. Okay? Guanidine. Okay. Oh, you guys have a book in the back, don't you? Miriam's got a book. Okay. Miriam, look up guanidine. Okay? Look up guanidine. And the question you have to ask yourself, does it have a charge on it? It does. In fact, doesn't it have a little plus or something? I wish I could do it how they did it, but they've got an NH2, and then they got all this stuff going on, a big blob of stuff here down here. But the point is, this is what it looks like. Okay. Listed in here, I just copied it here. This is listed here, copied here. This is the what form, everybody? Acid form. Has a plus. Is it neutral? No. It has a charge. So the name is always the neutral form. How do you make the guy neutral? He's going to have to lose more than a hydrogen. He has to lose a H plus. Right? Because that's what conjugate acids do. They lose an H plus. Right? So, okay. So he loses an H plus. Then you made him neutral. So the neutral form is going to be boom, boom, and H. All that stuff. Right? That's the neutral form. This is the conjugate acid or conjugate base? Conjugate base. Because he's going to grab an H and make this guy the conjugate acid. Okay? So the name always corresponds to the neutral form. So you got to make him neutral. He's the acid form. Rip off an H plus. This is the base form. Right? So guanidine is the base form. Guanidine is the base form. So if they say you have guanidine, they're talking about the conjugate base. Okay. Ethylamine. 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 Is ethylamine When I say ethylamine, am I talking about the conjugate acid or the conjugate base form? Oh, it has a charge. So that means, and remember, if it's in, all guys in the table have the big blue H's that are all the conjugate acid forms in the table. So the neutral form, she said it has a charge. It has to be the conjugate base. Because to make them neutral, you got to rip off that H+. Following me so far? Use the conjugate base form. All right. So if you got a book, you have a shot at this guy. Look up him and tell me whether he is, see whether he's a conjugate acid or a conjugate base. You don't have your book. How would you know? Where is it? Okay, who's got their book? Let's pick on someone who's got their book. You, Randy, you have your book. Okay, is 2,2-bipyridine a conjugate acid or conjugate base? It is a... Don't listen to her.
Well, I mean, it has a H plus.
It has an H+, so the name can't correspond to the plus form. The name can't, right? If you look in the table, it's got a plus on it, so the name can't correspond to the guy in the table, and the guy in the table is HA. So it has to be the conjugate base. Okay. So what's the point of all this? The point of all this is because if I say, and it's coming up, I say you have 250 milliliters of 0.2 or 0.89 molar ethylamine. All right? That's a big M. I'm saying I know the exact number of moles of the conjugate what form? Base. Right, that's not an F, that's an M. So I know I'm saying the conjugate base is that many moles. That's what it means. Okay. So that's why you really got to be able to identify from the name whether it's going to be a conjugate acid or a conjugate base. Okay. A solution contains 63 different conjugate acid-base pairs. Among them is acrylic acid and acrylate with the equilibrium ratio acrylate over acrylic acid of 0.75. What is the pH of the solution? Amanda? What's the big deal here? What is this trying to hit on? What's the 63 conjugate acid-base pairs have to do with anything? Nothing. Because remember when you could write all those 63 equations down. All those 63 equilibria. You could write them all down. It goes back to solving the full systematic treatment of equilibrium. It didn't matter what equation you picked. They're all equally valid. If you knew just one of them, one is just as valid as the other one. So if you know just the population of just one of these, right? One of these equations is just as good as the other one. They told you the ratio of the moles of the conjugate acid over the conjugate base. Sorry, the moles of the conjugate base with conjugate acid, right? Take the log of it, add it onto the pKa, and you have the pH. So that type of questions, they're just trying to hit on the fact that that's not important. Okay? Okay. Make sense? All right. How about this one? Describe how to prepare 100 mils. Now, I think in your notes you don't have 0.2 molar, right? 0.2 molar acetate buffer, pH 5, starting with pure liquid acetic acid, and solutions containing 3 molar HCl and 3 molar NaOH. Describe how to prepare. Describe how to prepare. The winner gets my favorite. I love these. Yeah, but you have to tell me.
Yeah, but you have to do it. You have to get the mold.
What is let me help you out a little bit. What is the formula for acetic acid? Oh, I don't know. All I know is that's acetate. So this must be acetic acid, right? Right. So you need 4 hydrogens, 2 carbons, and 2 oxygens, and you'll have the molar mass of the stuff. If you think you got it, just let me know. No clue? So what you go back to your notes here, where it said how to here, you have to figure out the mass, right?
Okay, which we do by doing. I thought this was your term.
Yeah, exactly. Convert the mils into liters, multiply by that guy. I don't. If first one to raise their hand and give me an answer. Okay, Kat, what do you propose?
You take 1.2.
She says take 1.2 grams of what? Of the liquid acetic acid. It's odd to take a mass of a volume, but it's true, it works, right? Just drip it out, right? Okay, she's going to take 1.2 grams of liquid acetic acid, then do what?
Dissolve it in water.
Okay, mix it. How much water? I'm getting the most from my M&Ms here.
100 milliliters.
Oh. What's wrong with saying 100 mils? That's going to be your final volume. Then when you start adding the guides, you're going to go over. So don't say 100, say...
Some random amount. Does it matter?
Well, kind of. Add...
Remaining?
I don't know.
Well, you don't want to say 100 mils because it'll go up to the mark. It really doesn't matter, right? Just so that when you add, you don't want it to be 10 mils, because look at all the water. Once you do all this work of getting it to be at the right pH, right? Once you do all this work to get to the right pH, and then you add 90 mils of water, the thing's going to move on you. So, I don't know, 90, 80, 70, a good amount, start out with a good amount of water, the majority of it, right? I'd say the majority. Because you're going to go through a lot of work to drip some NaOH, HCl, NaOH, until you finally get it to be the right pH. It takes a while. You got to have patience with it. You got to stir it up after every time you add some, and let the pH meter equilibrate and stuff. But she got the 1.2 grams part, right? So we'll give her the M&Ms for that, right? Does that make sense? So get the 1.2 grams, dump it in the majority of the water. I don't care, 80 milliliters. Doesn't really matter, but the majority. And then drop-wise, add HCl and NaOH, right, until you get the pH to be 5. Then you add the rest of the water. And you got it. Okay. Oh, we're about out of time. There's another question, but this is a good one. You should check out how to do this one. But how do you get rid of LOG? This is so folks remember how to do this. How do you get rid of LOG? Bump it up here. How do you get rid of that LOG? Raise both sides to the 10. That's how you get rid of LOG. And then that'll get you through the last one. I have 2 left. Who was complaining that I didn't hear him ever? Miranda was complaining. I give Big Bad John a hard time. Right? So have a good Halloween. I did hit record. Did I hit record? I must have.